It's Terry Dennery of the Math Works. So let's take a look at this simple demo. All right, so I'm going to hit the run button right here. And what we're going to see is a permanent magnet AC motor driving the movement of a constant inertia shaft, right? And we're going to see the blue and yellow line right on top of each other, and essentially perfect implementation of this movement. What we're looking at here is the voltage and the current, and I think it's very encouraging to see that our voltage settles into, as we reach constant velocity, kind of the sinusoidal shapes, 120 degrees apart that we expect for an AC motor. Right, so this is an AC motor. I call it an electric drive, and you'll see our mechanics is as simple as it gets. Constant inertia with perfect bearing, meaning there's no friction, no damping. And just to kind of provide a little bit more information, there's our AC motor. Here's our electric circuit connections to power electronics, which are like MOSFETs and things like that, that are going to be controlled by an algorithm, typically run on an embedded processor that applies field-oriented control. Now I want to show something a little bit more complicated, and this one will be a mechanism driven by the motor. Okay, here's a Simulink model, pure torque calculation assessed by our motion controller. There is feedback employed. There's a little bit more than that, which may be another video we'll get into at some point. But that torque drives the mechanism, and we see the movement that we want. And again, perfect accuracy as the blue and yellow lines fall on top of each other. Okay, so now let's drive it with an electric motor. So just copy this from my velocity control model. I will paste it in here, and then we'll set up our connection. Let's send voltage and current into this scope. And I'll see a few spikes and things like that that are a little bit of a problem for me. I'll even explain the reason why. This is a much smaller scale mechanical problem. Maximum torque requirements are like 0.3 Newton meters. So we'll rescale our electric drive. Maybe keep 30 volts, but let's have it be a stall torque motor of about 1 Newton meter. 2 radians per second should be enough. And that will reflect a pretty significant reduction in inductance. I think I'll use 4 pole pairs as well. And so we're seeing, again, nearly perfect performance on the movement of the shaft. We'll see the voltage and current calculated for us. And certainly as we are applying voltage to achieve motion, we're seeing how it expresses that torque required in the forms of the voltage and current profiles. Pretty simple demo. Main point, well, there's probably multiple points. Maybe the primary one is permanent magnet motors are awesome. And our ability to understand them and to control them is very significant at this point. And it's a tool like MATLAB and Simulink, which brings the mechanics, the electronics, the controls, and the software for implementing such algorithms onto embedded processors, just an amazing tool. So please contact us if you have this kind of application. And I'd almost say almost every engineering application there is now is going to be delving into this topic in one level or another. Okay. Anyways, thank you.